So today we are going to see about eukaryotic vector. Okay, so very important, little bit complicated. I want everyone to listen carefully first before asking question. Okay, so very important. So eukaryotic vector, here what we are going to see is especially with our prokaryotic, Saccharomyces cerevisiae. So you guys know that Saccharomyces cerevisiae is one of the most widely used and then one of the most important eukaryotic system in the biotechnology. Okay, so if you want to see this, how this eukaryotic vector was initiated, basically a discovery of a plasmid that is present inside a strain called Saccharomyces cerevisiae. Okay, so what they have done, when they are looking the Saccharomyces cerevisiae bacteria under electron microscope, so apart from chromosomal DNA, there was another set of piece of DNA whose size is 2 micrometer. So initially they have named it as 2 micrometer plasmid. That is how they find a plasmid inside the eukaryotic system. Did you understand what I'm saying, guys? From there only it started everything. So this is what they have isolated, the 2 micrometer plasmid, which is 6 kb. So how now? So this is your Saccharomyces cerevisiae. Inside there was a chromosome, and then inside there was a small bacteria, so plasmid. Under the microscope, the size of this plasmid is 2 micrometer. That is the reason why they have named it as 2 micrometer plasmid. But when they isolated and then they have seen, they sequenced it, it is around 6 kb length. It has REP2 region, FLP2 region, FLP region, D, and then origin of replication. So if you see that this REP2 and then REP1, so it is inside here, yes. REP1 and then REP2, both the sequence are involved in the replication of this plasmid. Okay, so whereas this FLP protein or FLP sequence is the one which is involved in the conversion of A form to B form. Okay, so whatever you are shown here is A form. The B form, what is the difference between A form and the D form? There will be rearrangement of the position of this REP2. REP2 will be here, REP1 will be here, FLP will be here, and then D will be here, like that. Understood? So that is the difference between the A form and then B form. Till now we have no idea about what is the function of D. One more time, the size of the isolated 2 micrometer plasmid is 6 kb, and then it has four genes. One is REP1, REP2, both of them are involved in the replication. FLP is the one which is involved in the conversion of A form to B form. The role of D is unknown, and then it has origin of replication. So by seeing the function or the characteristics of this particular plasmid, can you say that this plasmid is useful for cloning? I'm getting answers like this. No, rarely. Very good, Preeti. Excellent. Very good, Neelo. Very good, Chetana. Very good, Narmada. Very good, Roja. Very good, Surabhi. Why I am saying these people good, na? They are saying that this cannot be used as a vector for cloning because it does not have any restriction site and selection marker. Very good. Understood, others? So, in order to utilize this particular plasmid for cloning in eukaryotic system, people started engineering it. That is what we are going to see next. Yeast 2 micrometer plasmid. It is excellent for cloning. It is 600 base pair. So it can have a copy number of 70 to 200. Is a very high copy number. So like others, what about selection marker? This is very important. Even if I can clone, I need to identify the recombinant DNA. So here I want everyone to listen carefully. Normally, a yeast Saccharomyces cerevisiae use a gene called LEU2. Okay, this gene codes for an enzyme that is involved in amino acid biosynthesis. Okay, one more time. In general, Saccharomyces cerevisiae uses a gene named LEU2 gene. This is the one which is involved in amino acid biosynthesis of leucine. Okay, understood or not at this point? So people started thinking, why don't we use this leucine as a marker? So basic idea is, from the yeast chromosome, they removed minus LEU2. They removed this LEU2. After removing this gene, they inserted into this 2 micrometer plasmid. So now this Saccharomyces became auxotropic mutant. What is meant by auxotropic? Na? This particular Saccharomyces cerevisiae will grow only if leucine is sublimated externally into the medium. Yes or no? Guys, understood or not what I am saying? Can I have a response from everyone? Is there any problem for others to understand or to imagine? Okay. Nothing the story. I'll show the another one. So in order to use this leucine as a gene for, same thing I'm explaining, guys, those who want to repeat, the leucine, they have removed the leucine, that is leucine minus, can you see that leucine from this Saccharomyces cerevisiae? That means this chromosome contains no leucine gene. Okay, which means that this means that, Chaitanya, just listen na, what I'm saying, please. So now this bacteria will grow only in a media that contains leucine, or else it will not grow. That is called auxotropic mutant. This point you understood, Rajesh? Smita, Shruti? Now, after removing this leucine 2, they inserted the gene into the plasmid. Okay, now the vector carries the leucine gene. So now the vector, if you insert any DNA of my gene of interest, if it goes inside this bacteria, this can grow in a media that contains no leucine, isn't it? Understood or not what I'm saying? So one more time. So this is what, based on this, they have constructed a 2 micrometer plasmid. Narmada, just listen. The same thing I will repeat one more time. Wait. So they have taken, this is the leucine gene which is present in the bacteria, the plasmid. They have taken the 2 micrometer gene. They fused with another plasmid called PBr322 plasmid. Okay. Now you know that this PBr322 is prokaryotic vector, whereas this 2 micrometer plasmid is eukaryotic vector. Since you engineered a plasmid in such a way that it contains both PBr322 leucine, it can grow in both the hosts, that is prokaryote as well as eukaryote. If any plasmid that grows in 2 different hosts means, what is the plasmid called? Very good, Neela. That is called shuttle vector. This name of this plasmid is called YEP13. Okay, so now this plasmid has origin of replication, it has selection marker, it is metabolic marker, and then it also has multiple cloning vectors. Okay, Narmada, Namrata, you didn't understand the same thing. This is the pictorial representation. Okay. So if you see that in this YEP, the yeast episomal plasmid, so we have inserted a gene of interest here. Okay. Understood? This is a plasmid with gene of interest. This is self-ligated plasmid. Okay. Since this plasmid is a shuttle vector, first we are using tetracycline as a marker. You see here. So first we are inserting a DNA into this tetracycline portion. So that is what it clearly shows here. The gene of interest is inserted in between the tetracycline gene. So initially it is resistant, it is resistance. When I insert any gene in between the tetracycline, what will be the condition here? What will be the phenotype of this plasmid? Ampicillin resistant, tetracycline sensitive. Very good, Neil. Very good, Smita. Okay, because I have inserted DNA in between the tetracycline, this tetracycline become sensitive. But whereas if it is self-ligated, what will happen? Still this tetracycline will be resistant. So here, what I am trying to do here is, I am going to plate this type of bacteria in a media that contains ampicillin. Okay, because here ampicillin is still it is resistant, isn't it? So, but tetracycline sensitive. Understood? Understood or not, guys? So after growing, again I will isolate the plasmid from the bacteria. Now I will transform into the yeast. So in the yeast, what will happen now? The plasmid contains LUU gene. Now, because the chromosome contains mutated LUU gene. So once it goes inside, it undergoes homologous recombination and then gets integrated into yeast chromosomal DNA. So it will become a part of the chromosome. Another type of chromosome is yeast artificial chromosome. So mostly this type of, we can see that it is an artificial chromosome, very, very big. So this particular chromosome will have yeast telomerase. You must have studied in the eukaryotic gene system. If not, it will be revised in the unit 4. Yeast telomerase at each end. It has yeast centromere sequence. It has selection marker, exactly like what we have seen. It is amino acid dependent. It also contains autonomously replicating sequence ARS, and then it is also contains a restriction site for DNA ligation. It can hold a very, very large piece of DNA from 200 to 2000 kb, which can hold very, very large size of the DNA. Clear? So the next type of plasmid is expression vector. Till now I have shown everything. It is a cloning vector, which means that the DNA will be there, that's it. It will not express. But there are some plasmid where if you see that it will have an origin of sequence, antibiotic, but in front of my gene of interest, if you add promoter, now this thing will become expression vector. This promoter will decide. It can be engineered in such a way that it can also express only a tissue specific expression. Tissue specific expression can be done like this. You can see that the green fluorescent protein is cloned into a vector which contains a promoter which will express only in the eyes of the mice. You can see the whole body is expressed. The whole pig body is expressed. The whole mice is expressed. Okay, so not only the green fluorescent, it can be yellow, cyan or blue color. Any type of protein can be expressed. Here only they have shown because it can be visually seen like fluorescent proteins. Exactly, Nitish. Any questions, guys, till now? That concludes your plasmid. Next, I am going to show a group of scientists. These are the people who have developed a green fluorescent protein. Very, very recent. It is in the year 2008. They got a Nobel Prize for this. Okay. Guys. So till now, what we have seen how to isolate DNA. We have seen how to manipulate a DNA, and then all the very important things we have seen about a plasmid that carries a gene from one system to another. With this plasmid, the application of very important application of the plasmid is recombinant DNA libraries. Anybody here who has created DNA library? I know only the book library. I don't know anything about DNA library, isn't it? Guys, I am asking a question. Have you ever tried creating a DNA library? Yes or no? Answer is very simple. Anyone you have to choose. DNA library means it is a collection of cloned DNA fragments. Two types of genomic library can be created. One is DNA, that is gene. And then cDNA library. Two types of libraries can be created. First, we will see about genomic library. So basically, recombinant, there are two types of DNA libraries. One is genomic or chromosomal library. Other one is cDNA library. That is what I have told. This is the whole genome. Okay. It is very, very difficult to understand what is the sequence present. So that whole genome are restricted with restriction enzyme in order to create a small pieces of genomic DNA. So you guys already we have seen what is a restriction enzyme. So now this is what the role of restriction enzyme it does. It cuts into different size pieces. Now this is the plasmid we have seen. So using the same restriction enzyme we are going to cut it and then we are going to ligate this restricted DNA into the plasmid. You can see that, yes, with the ligase. Yes, this is 1, 2, 3, 4. So now all these 3, 4 plasmid all together make a DNA library of the original one. So now it has been transferred into bacteria, each plasmid into one bacteria. So now all this bacteria carries a genome. So now I can study the function of each and every gene. Got it? So this is the bacteria which grows. Understood? Any question, guys? If Gayatri has asked a question, how can we make sure that none of the fragment is missed? Yes, Rajesh, we can. Right? That is a very good question, right? So what she has asked now. If this is the DNA, if I cut into 4 pieces, so how many plasmid I need? 4. So if I insert into 4 plasmid, I will create a complete genome of this sequence, right? Understood? If huge genome which is around 3 into 10 to the power 4 kb size, how many pieces it will come? Any idea? It's very difficult, na? Okay, have that on your mind. Next one. If let us take a small one, it produces 1, 2, 3, 4 fragments. If I get only 3 fragment, which is around 75% recombinant library, right? Isn't it? If I get 4, 100%. If I get 2 plasmid, 50%. We can calculate now. So, in order to get an idea about how we know now, there is a formula. Okay, I'll show you next slide. Okay, the formula is coming. Before that, in the animation I showed that the DNA fragment can be made into pieces. For example, I showed restriction enzyme, isn't it? Apart from the restriction enzyme, there are so many other ways where I can create a fragment. Okay, so the DNA fragment can be created by restriction endonuclease digestion. It can be by mechanical steering. It can be by cDNA synthesis or chemical synthesis or PCR. Any one of this method will create a piece of fragment, isn't it or not? Yes or no, guys? So once I produce the fragment can be it has to be ligated into the plasmid. That can be ligated using a homopolymer tailing or ligating cohesive terminal, that is sticky end, or it can be blended ligation or linker molecule or TA cloning. Any one of the method can be used in order to insert a piece of DNA into a plasmid. After that, this plasmid has to enter into a bacteria. That can be done by transfection, or it can be done by a transformation, or by in vitro packing. So once you have done, the selection of recombinant DNA can be done by hybridization method or PCR method, immunochemical, protein-protein interaction, protein ligand interaction, functional complementation, gain of function. So these are the different ways by which I can screen the cloned DNA sequence. Did you understand the complexity of the DNA libraries in the preparation? Guys, do you understand, yes or no? Any questions? Let me know. I am again asking the same question. What is the significance of adding antibiotic resistant site? What is the significance of adding antibiotic resistant site, guys? Screening. Very good, Neelam. Next. Anupama, it is used only for screening purpose. Understood? Very good, Smita. Still you have a question, guys? How will you know which gene contains, which plasmid contains Yes, Arthi, your question is correct. It is used as only as a vector. So Gayatri, there are other means by which to know. I will be explaining that on the next slides. Okay. Okay. Nitish has asked what is mean by TA cloning. What is TA cloning, guys? Any idea? Cloning without restriction enzyme. Very good. Nitish, understood? Okay. Till now, any question, guys? Till now, any questions? Next, little bit more complicated version we are going to see. That is genome size of a selected organism. So E. coli, the size of the genome is 4 into 10 to the power 3 kb east. You can see the different sizes. So if I want to create a genomic library of this restriction of this Escherichia coli using a particular restriction enzyme, if I want to create 100% genomic library, how many plasmids I require? Can anyone say? For example, restriction enzyme EcoR1. I'm using an enzyme called EcoR1. I want to create a library of Escherichia coli. If I want to create 100%, which means that each and every small bits and pieces also I did miss it, then how many plasmids are required? Any idea, guys? Can we calculate that? Yes or no? No, yes. How? How can you do that? There is a formula for that. This is the formula. Based on this, there was a one question in the exam, very easy, very simple. Probability of having at least one copy of any DNA sequence in the genomic library. N is equal to inverse logarithm of 1 minus p divided by inverse logarithm of 1 minus a by p. Here in is natural logarithm or inverse log. N is nothing but a number of clones that are required. P is nothing but the probability. A is the average size of the DNA fragment inserted. B is nothing but your total size of the fragment. Understood? Have you noted down this formula, guys? No response here. I don't know what. You guys are sleeping? Guys, are you sleeping? Writing. Very good. Okay. Okay. So this is the question. Can anyone solve? Not anyone. Everyone solve. So here I say that probability P. Na? So let us take 95% is the probability. Calculate for this. Okay. Calculate taking P as 95 percentage. Let me know who is going to tell me the answer first. I'll give you 2 minutes or 3 minutes maximum. Try here, Nitish. You have a formula. Try it. If you didn't get it, then I'll show you. You want to see the formula once? Yes, this is the formula, guys. Anybody got this answer? This is how it has to be. So I told 95 percentage probability. So 95 by 100, that is 0.95. 1 divided by A by B. Okay. So if you add that one, you calculate. Yeah, this is what actually this is final version I am showing. Inverse of 1 minus A by B, you will get that one. Okay. So this is what, just calculate, you will get the answer. Okay, so I showed the answer, work out, you will get it. I am not keeping 1 as A, that is a simplified version. Okay, the same way if I increase the probability 2, so here what I want to tell you is this size 95% if I want to cover, I need 4.2 into 10 to the power 5 clones. If I want to cover 99%, then I need 6.5 into 10 to the power 5 clones. Just I want to show you the complexity of DNA library creation. Just note down the question and then try when you guys are free. Okay, next. So since we have any question, guys, did you understand what I'm saying? Everyone? I got response only from Ramya. The rest all are sleeping. Gayatri, it is not one, it is a simplified version I'm showing. After simplification, if you divide A by B, 2.8 divided into 2 to the power 6 divided by 1.4 into the power, you will get this mark, this one. Okay? It is not, I am not getting this one. Okay? It is simplified after plugging into the formula. So since I told you that each and every plasmid has a different holding capacity, I told you na. So if I use a genome size of 3 into 10 to the power 9 base pair, okay, if I expand, this is what, this many base pair. If I use lambda as a vector, which I can insert up to 20,000 base pair. If I want 0.5 probability, that is 50% probability, I need this many plasmid. 0.9, I need this many plasmid. 0.99, I need this many plasmid. 0.999, I need this many plasmid. The same way, if I use yeast artificial chromosome, just imagine for 0.99% itself, I need only around 20,000 clones. See the difference between this plasmid and then this plasmid. Why we took 95%? You can take anything. You can take 0.5, 90%, 95%, 99%, doesn't matter. I think you didn't get the idea why 95%. 95% is, if this is the size of the genome, at least to cover 95% of my sequence, how many clones I need? At least 95, but I expectation is 99%. Why 99 here? If I want 95%, I need only this many clones. If I need 99%, I need this many plasmids. Okay. I will end the class. This is the answer. Yeah, this is the final answer, Syed. That is, Syed, still you didn't understand what I am trying to say here. Okay. Okay, this is the genomic sequence. Okay. I cut into 4 pieces. Let us take 5 pieces. 1, 2, 3, 4, 5. Let me take one more 6. Instead of asking how 1, Nudana, why don't you calculate using this formula? This formula I have given. I have explained each and every variable. I have given all the numbers, and then why don't you plug in and then play? If you do that, you will get the answer why I am getting 1 divided by 1.4 and 10 to the power 5. This is, don't think that I added 1 divided by 1.5, 4.5. If you simplify A by B, you will get this answer. Find out how. Okay. Syed, if I cloned only 5 fragment, how many percentage I have covered? Out of 6, yes. %83, very good. If I want to cover 100%, how many fragments I want? 6. Did you get? If I want to cover 95%, I need 4.2 into 10 to the power 5 number of bacteria. That is, each bacteria contains one plasmid with one piece of DNA. Can you correlate now? Syed, if I want to use but 95% is not asked the question. That is the reason I told take it as 95, because people will always assume, see, it is not required that it is 95 is required. It's a general question. The P can be taken anything. Even you can take 50 and then calculate. The answer is going to be the same. It will be different. Even you can take 70% and then calculate. I told initially take 95%. Did I say or not? Okay. Guys, you guys must have taken snapshot. You calculate. When you are free, you will find out. Okay. In human sequence, which plasmid is used? This is human genome only. Chitra. They have used BAC and then YAC. Okay guys, I will end the class here. Tomorrow we will meet.